Kasapeteva. I'm a PhD student in the Institute of Electronics of Bulgarian Academy of Sciences, and I'm going to present our work, Nonparaxial Optics and Broadband Optical Solitons. So let's begin with something in between an abstract and an introduction. So in the recent decades, the interest of scientists in the phenomena resulting from the evolution of broadband laser pulses has significantly increased. And it is easier for us to obtain phase-modulated femtosecond pulses or even reach the attosecond regions, where the spectral bandwidth of the optical pulses is of the order of the carrying frequency. And this type of light pulses we call broadband ones. We have all heard about the nonlinear Schrödinger equation, and it really well describes the propagation of narrowband optical laser pulses. But for investigation of the evolution of broadband optical pulses, we need something else. And that else thing is the generalized nonlinear amplitude equation. So it differs from the nonlinear Schrödinger equation with two additional non-paraxial terms, which I'm going to show you next on the slides. So what is the advantage? What makes the nonlinear amplitude equation so important and different? Well, it can be used to describe both narrowband and broadband pulses. So right here, you see, we have found a new analytical Soliton solution of the generalized nonlinear amplitude equation. And then this result was compared with the well-known Soliton solution of the Schrödinger equation. So when we talk about fundamental Soliton, it is shown that the main difference which happens between the two solutions from the amplitude equation and from the Schrödinger equation, the difference is in the phases of the pulses. So this changes considerably the evolution of the laser pulse of the Solitons. So right here, you can see below one graphic that shows how we can get Soliton. From one side, we have the abnormal group velocity dispersion, and from the other side, we have the Kerr-type nonlinearity. When we sum them up, we get a Soliton. Right here on this slide, you see a picture of a man. His name is John Scott Russell. He was a Scottish engineer and naval architect, and he is considered to be the founder of Solitons, of the first Solitons, let's say. Of course, I'm not going to read out loud this whole quote, but the most important thing is that he saw the water forming strange waves in the canals in Scotland, and it made such a huge impression on him. And he got on his horse just to trace them and see what are these waves doing. Back then, he called these waves large solitary waves. The term soliton wasn't invented back then. And later on, when John Scott Russell was interviewed, he said that the day he found the solitons was the best day of his life. It's an exact quote of his words. So let's see this timeline and trace what's going on with the solitons throughout time. In 1965, Zabursky and Kruskal find a solution to the Kuiper-de Vries equation, which describes the propagation of solitary waves in shallow water. And it is used by these days, as far as I know, in hydrology. In 1973, Hasegawa and Tappert predicted the existence of laser solitons when we talk about optical fibers. And their studies were based on the nonlinear Schrödinger equation, which you can see down below, and its solution also. In the 1980s, were conducted the first experiments to generate and propagate optical solitons in single mode silica fibers. So right here, you see written, let me just put on my laser pointer. I think you can see it. Yes. So in order to investigate the propagation of femtosecond and attosecond optical pulses, we need to use, as I already said, the nonlinear amplitude equation. It was obtained by Akhmanov and Chirkin in 1981, and you can see it written right here. If you remember, I told you that the amplitude equation differs from the Schrödinger equation by two non-paraxial terms. I talk about these ones right here. Why do I talk about them and why it is important to mention them? Because here we have one alpha, you can see it right here. And this is a parameter which, let's say, determines whether if this whole thing here would be paraxial or non-paraxial. And the alpha depends on the duration of the pulse we use. So if we use a duration of nanoseconds, let's say some nanoseconds, here it's written 70, it doesn't actually matter, we need nanoseconds. This won't be significant, and we will get the paraxial case, but it's not what we are talking about right now. We need the non-paraxial case. Okay, so this is the solution as follows of this nonlinear amplitude equation. So here on this slide, you can see the numerical solution of the nonlinear amplitude equation for fundamental soliton. And what actually do you see on the figure? Here you see the intensities of the fundamental soliton, and it is shown in different cases. What's the difference between them? In the first case, here in A, we have duration of the pulse of 35 femtoseconds. Here we have 25 femtoseconds, and here we have 15 femtoseconds. And as you can see, there is a shift in the peak of the pulse. So it is seen with bare eye. No need to explain further. So this table right here shows the shift in the position of the soliton peak in time when we talk about pulses with different initial duration and this carrier wavelength, 1.5 micrometers. We talk about propagation in single mode silica fiber. Here you can see solitons of higher order. Again, on this figure, you see the first, the profile of intensity, and then the spectrum. And here we have a pulse with duration 300 femtoseconds. The order of the soliton is the second. And now I'm going to show you what big difference makes the duration of the pulse. So just compare the two pictures. We have here the second order solitons. Again, we have here the second order, but the duration is different. And you can see that the figures are completely different from one another. Here you can see the intensity profile. Here you see the real field of the soliton, and then you see the spectrum. Again, it is of 14 femtoseconds duration. Enough about the second order solitons. Now let's talk about the third order. You see two pictures, let's say figures, figure 4 and figure 5. You see again the evolution of the intensity profile and the spectrum. So here is the intensity, here is the spectrum. And it is good that these figures are one by another, just to compare. In the first case here, we have duration of 250 femtoseconds, and here we have 14 femtoseconds of duration. And you can see how different from one another are these cases. We are getting even higher, and we're going to talk about solitons of the fifth order. You can see right here significant changes. So again, here we have intensity profile and spectrum of the pulse. Here we have duration of 250 femtoseconds, and here we have a duration of 14 femtoseconds. Up to now, we have been talking about bright solitons, but you know that there are different types of solitons, and another type of solitons are the dark ones. So what are they? The dark solitons, they match with the solution of the modified nonlinear Schrödinger equation, when the dispersion of the medium is normal. It's a really important factor to check the dispersion. So when it's not normal, not possible to observe. So the propagation of the dark solitons can be described by this equation right here. And what is the big difference between the bright and the dark solitons? I'm going to tell you right now. When tau, a function connected with time, it tends to 0, the amplitude function of the bright solitons also tends to 0. And that is the main difference between bright and dark. The dark solitons, actually, they have fall of the intensity. And in order to characterize this depth of the fall, we need to include a new parameter, let's say. And when this parameter equals to 1, the intensity is 0, and we have a completely black soliton. But when this parameter B is lower than 1, the intensity is not 0, and the soliton we have is gray. Here you can see two graphics. They represent numerical calculations, and they show the evolution of dark solitons in single mode optical fibers. In the first case, we have pulse which under which envelope we have oscillations. We have 4 oscillations. And in this case here on figure 9, we have 20 oscillations below the envelope of the pulse. And you can see the big significant difference in the intensities of these two dark solitons. So up to here with the theoretical part, let's say, but how and where can we use the solitons? First of all, I'm going to mention the application in optical communication systems. So I bet you know it, but let's say it one more time. The solitons give very good opportunity to transfer data on very long distances without significant loss. They're very reliable, and that's why they're used. They can be used in photochemistry, in lidar systems or sensors. We heard a talk here in this session about surgical operations, ablation, and so on. And of course, they can be used in nanotechnology. What can I say in conclusion? It is shown that the nonlinear amplitude equation has exact analytical soliton solution, and it correctly describes the evolution of both narrowband and broadband pulses. And the main difference between the generalized nonlinear amplitude equation and the nonlinear Schrödinger equation is the pulse phase. So it has been demonstrated that for optical pulses with large number of oscillations below the envelope, the evolution of narrowband nonlinear amplitude solitons coincides with those obtained by solving the Schrödinger equation. So we have observed a significant shift in time to the position of the peak of the soliton. When we talk about the evolution of higher order solitons, we have studied it numerically, and you saw many figures of that. And it is shown that the dynamics of spectrally narrow pulses, it matches with that described with the nonlinear Schrödinger equation. But when we talk about spectrally wide pulses, we get decay and a whole new type of dynamics. The present paper is supported by the Ministry of Education and Sciences. And last but not least, I would like to thank you for your attention.